then they'll start aligning with your packets. So don't let the numbers confuse you. Okay, now let me share it. Sorry. All right. Can y'all see this okay? I know it's just a blank screen, but we're on that first question. Yes? Okay, perfect. So let's go ahead. I'm gonna expand it real fast. Give me 2 seconds. Okay. So just like last time, I'm gonna have y'all go ahead and work on the problem, and then we will discuss the answer and why that answer is. So go ahead and answer this first one, and then we will discuss. When y'all have the answer for the multiple choice, you can just type it in the chat. For the ones that are free response, you can go ahead and just say done. But yes, okay, go ahead. Okay, so let's go ahead and talk about this one. This one really, it kind of goes back to when we were just talking about some trends and compounds and how they form, but there's a common, not trend, but relationship here between molar mass and boiling point. So what you should know about the relationship between molar mass and boiling point is that with an increased molar mass, you have an increased boiling point. So that would just be, to answer this one, you would have to go ahead and calculate the molar mass for each of these using the periodic table masses, and you would come out finding that Cl2 is going to be the one with the highest boiling point because it is the one that is the heaviest or has the largest molar mass. Okay, so that's, okay, so I see what y'all are doing. Y'all are pulling from the last chapter. And if it talks about intermolecular forces in the question, then y'all usually have to apply the hydrogen bond and that stuff. But this one is one talking about molar mass specifically because it doesn't refer to those intermolecular forces. Does that make sense? So if we were talking about, if we're talking about intermolecular forces. So usually they'll say like based off of intermolecular forces or using the rules of intermolecular forces, which the below has the highest boiling point. And in that case, A would be the correct answer because of the hydrogen bond. But in this case, because of the relationship between molar mass and boiling point, which you learned it should have been like the first exam, I want to say, the answer for this one should be based on molar mass, which is Cl2. Usually in the ones with intermolecular forces, they're going to specify that you're going to be expected to use the intermolecular forces. Does that make sense? I've almost cut this one out before just because it does have that problem, but this is the trend between those two. Okay. All right, so let's go ahead and do this next one. Yeah, that's what I would do. Usually they'll be pretty specific. This is the reason I should have just edited the problem so it was more specific to molar mass, but I believe that on your exam problems, they'll kind of lead you in the right direction. So I should have edited this one so it was a little more clear they were talking about molar mass, but it can go both ways. Okay. All right, so this next one, I'm gonna tell you right now, on my key, I didn't write the brackets with this negative sign around it. They are there, so I'm gonna try my best to draw them in, but I just forgot to write it in. So there should be 3 resonance structures for this one. So go ahead and draw those resonance structures. Make sure you include the brackets around the structures with a minus sign, okay? So that's something I failed to do, but they should be there in the answer. And then just let me know when y'all are done. And for those of you that didn't hear me at the very beginning, this file that I'm about to send is the final review. So it's going to be everything compacted. We're not going over it today or at all. It's more of just a study guide for y'all. Also, another good thing to note about the questions I have on here, a lot of the multiple choice I took directly from past final exams. So, and I also mixed it in with some free response just because I know that y'all have had free response in the past, and they weren't 100% sure if they were going to do just multiple choice or just free response or a mix. So I just kind of wanted to provide a little bit of everything for y'all. All right, would anyone like more time? All right, perfect. So let's go ahead and start talking about this one. So like I said, there should be 3 resonance structures. And I mean, it's hard to kind of just talk y'all through this, so I am going to just go ahead and show you what I have. Remember again that I missed the brackets on these. So we have 3 possibilities. You can have 2 double bonds between the sulfur and the nitrogen, or you can alternate between having 3 between nitrogen and sulfur. These are the 3 possible resonance structures, okay? And again, just so y'all remember that with these problems, we need to have, I'm not going to draw, okay, wait, that's in white, hold on. My bad, sorry. So, wait, why is it still doing that? There we go. You'll need to draw the brackets around these with a little negative sign here, and that would be for each one individually, okay? I don't know why that's not in black anymore either, but it's fine. I think y'all get the point. I don't know why it's being all finicky. But do I have any questions about how to draw these resonance structures? So really the most important part for anyone who is a little bit confused on it is just to make sure that you are calculating the total number of valence electrons for each individual. Yes, sulfur can have a triple bond. As long as it's appropriately lined up with however many lone pairs it has, right? So technically we are completing sulfur's octet here. 6 of its electrons are here and 2 of them are here, giving it a full 8. So although sulfur, we've said that sulfur, I mean, with anything that has the availability to bond, as long as it has an octet, it can bond multiple times as long as it's not going over its octet, right? So we have a lot of different atoms that can bond 3 times. I know I've said commonly nitrogen likes to bond 3 times, but that doesn't mean it has to always bond 3 times. It can bond twice, it can bond once. Same thing, if sulfur tends to like having 1 to 2 bonds, it doesn't mean it can't bond 3 times as long as the lone pairs are located. C is a central atom, kind of because of electronegativity. It should be the least electronegative out of these ones, but it's also based on group number and availability to bond. So if we go up to the periodic table real fast, it is the least electronegative, and that's a big reason as to why it tends to be in the middle. But if you also look, it has a lot more availability to bond as well. It has 4 options to bond, meaning it has 4 valence electrons, and it can share more. But yeah. How do we know to do triple and single instead of a double bond or something else? Okay, let's go back down here, sorry. So we know to do, okay, so we have, okay, so I think I understand the question. So it says, how do we know to do a triple and a single instead of a double bond and something else? So really it all comes down to making sure that we have a full octet, right? So if I did, I have 2 doubles here and that creates a full octet around my carbon, right? Well, you can't put a triple and a double. You only can do a triple and a single because this triple bond gives carbon 3 bonds, and then the single bond gives it its 4th bond. So if you do a triple and a double, carbon has exceeded its octet, and it's not possible. So your really only options are triple or single, and double. Does that make sense? So you just have to really make sure that you're not going over that central atom's octet number, and that's why we do these ones. Okay, do I have any other questions on these? It's just really important that you know how to draw a basic structure for a compound. Make sure you know where those electrons go. Okay. So let's go ahead and do this next one. What is the strongest intermolecular force between this compound here? And y'all can just type that answer into the chat if you would like. Awesome. So I'm saying the correct answer. my way of circling it was just to kind of identify those stronger bonds, but the answer should be hydrogen bond, right? We have our regular, we have our other intermolecular forces, just, but the one that is the strongest that y'all should be familiar with is our hydrogen bond, right? And our hydrogen bonds are between which things? Hydrogen and what other three atoms? Do y'all know? Yes. Yes, F, O, and N, right? So this is a hydrogen bond as well. And then what kind of intermolecular forces are found in every single compound? Ones that are in every single compound. Anybody? Yes, dispersion forces, right? So dispersion forces are LDF. So there's London. They're technically called London dispersion forces, but dispersion is the same thing. And those will be found between basically in every single compound, right? And those are going to be the weakest, but they're all there. Okay. All right. So that is the answer: H bonding or hydrogen bonding. All right. Okay. This next one. Do you have any questions on that answer? Hopefully that one was pretty straightforward. It's kind of in the last chapter y'all went over. Okay, so if you have 25 grams of C2H6 react with 56 grams of O2, how many grams of CO2 can be produced? And when y'all are done, go ahead and let me know so I can kind of gauge where we're at. Oh, and one other thing, if we are not able to get through all of the problems on this packet, I'm not just going to not finish it. I will let y'all see the answers for the problems we don't cover. I don't want to just leave y'all hanging without those answers. But I recommend doing them without looking at the answers and then checking yourself with the answers that I give you. No, wait, Tyler, we have a couple more people who are done, and then we'll go ahead and review. Okay. So let's go ahead and talk about this one. What type of problem is this example? Yeah, exactly, limiting reactant, right? So the first thing you should probably do is write the balanced equation, what is the equation that we're dealing with here going to be an example of? Just one of the types of equations. Combustion, right? Exactly. So although it doesn't tell you that water is a part of this equation, you should know that if we have a hydrocarbon like C2H6 reacting with oxygen or O2, that we should be producing both CO2 and H2O. Okay, so they don't have to tell you that hydrogen's a part, not hydrogen, sorry, water's a part of it. You should still include that in your balanced equation. So I put the work for this problem down here, so give me just a second. This is the equation that y'all should have come up with. It's balanced, and it is a limiting reactant, right? So the first thing I did here was I found my C2H6 first, right? So I converted my 25 grams of C2H6 into CO2 because that's what I'm focusing on. The question does ask how many grams of this and how many grams of CO2 are produced when these two are reacted. So that's why I'm converting it to my CO2. So you should have gotten around 1.66 moles of CO2 produced with 25 grams of C2H6, okay? Just remember, we have a molar mass conversion here and a mole to mole conversion here. So we get this 2 from our 2 moles here, and we get this 4 from our 4 moles of CO2. So we have a question, how do we know it's CO2 and H2O again? We know those are products because the equation for combustion is always the same, right? You'll always have a hydrocarbon, which is just a whole bunch of carbons and a whole bunch of hydrogens in a compound. So this is a good example of a hydrocarbon. The hydrocarbon will always be added to or reacting with an oxygen or oxygens here, which is always going to be O2. And it will always produce CO2 and H2O. So it's just something you need to memorize. Combustion reactions will always produce CO2 and H2O. Hopefully that answers the question. Okay. And then the second part was I had to convert our given oxygen, right? So we have 56 grams of O2, and I went ahead and converted that. We did a molar mass conversion. Please remember, if it's giving it to you in terms of O2, you need to make sure that you're multiplying that by 2 because you've got 2 oxygens as a part of that compound, right? And then we convert with our mole to mole conversion, which is 7 to 4 based on the balanced equation. And you should get about 1 mole CO2. Maybe I rounded a little bit, but again, it's just basic rounding. It's okay. Unless the problem's asking specifically for you to be on track with your significant figures, then don't round. Make sure you're counting your significant figures in each step, okay? So in this case, it didn't specifically ask for sig figs, so that's why I didn't use them. And then, as you can see, I circled this one because remember our limiting reactant is 1 mole, right? So that means that our O2 is our limiting reactant. So this is the one we're going to use to convert to our mass, right? So that's what I did next. In my next step, I took this 1 mole of CO2 and multiplied it by my grams of CO2. And that should get you about 44.01 grams of CO2. So do you have any questions about that and how we do our limiting reactants? Hopefully not. Okay. So if y'all don't have any questions, I'm gonna scroll back up because that's where the next question is. I just had to do my work below. So, and if you guys do need me to come back to any of these problems at the end, you can always ask me to. So let's go ahead and look at this question here. I believe this is question 5 on y'all's packet. So a layer of copper welded to the bottom of a skillet weighs 125 grams. How much heat is needed to raise the temperature of the copper layer from 25 degrees Celsius to 300 degrees Celsius? The specific heat capacity of Cu is 0.387. And then take a minute. When y'all are done, go ahead and let me know. Real quickly, just to make sure we're all on the same page here though. When we're talking about specific heat capacity, which equation do we use? Because remember, we have specific heat and then specific heat capacity. So which one do we use for specific heat capacity, or lowercase c? Yes, Q equals MCAT, right? Perfect. So Q equals MCAT is the correct answer. And then if they ask you, if they tell you, or they start the question off by saying either bomb calorimeter or coffee cup calorimeter, which one of those two calorimeters corresponds to specific heat capacity or Q equals MCAT? Which type of calorimeter? Exactly, coffee cup, right? Okay, good. Just making sure we're all clear on those little connections there, because they do matter. Okay, I'm gonna wait for a couple more dones and then we can talk about it. Does anyone want more time? Okay. All right, and if you ever do want more time, just tell me. There's no pressure to be done super quick. All right, so like we discussed, this should be a Q equals MCAT problem, right? We have everything we need. We just need to make sure that we're talking about the change in temperature, right? That's what the A in MCAT would stand for, delta T, right? So make sure you're converting that to Kelvin and finding the change, and then mass for the M, and then our little c for this heat capacity. So Q equals MCAT is the equation I wrote down, and then I plugged everything in. I'm sorry if my handwriting's a little messy, but this is just 125 grams times our 0.387 for our specific heat capacity, and then 275 was the difference that I got between those two temperatures in Kelvin. Okay. And then from that, I got my answer was 1.33 times 10 to the 4th joules. Do you have any questions on that one? It's always good. I know I started putting my units in here and I kind of trailed off here and didn't finish them, but a good way to know if you're doing it correctly is to make sure that your units cancel out appropriately. So if you had brought these units down here, you would see that my grams on the top cancels out with my grams on the base of this one, so that gets rid of grams. And then I have Kelvin here canceling out with the Kelvin on the bottom, leaving me with joules. So if you ever forget the equation, sometimes your units are really helpful in helping you remember. It doesn't necessarily need to be in scientific notation unless they ask for it in scientific notation. But again, your professors should accept both answers because they're both technically correct unless they specify, okay? So personally, I like scientific notation a lot better. It's a lot cleaner to me, in my opinion. And I tend to leave off like zeros sometimes if I'm doing it in a non-scientific notation. So that's just a personal preference, but unless they specify it. Okay, any other questions? So why don't I convert it to moles? So again, for this one, it's the M stands for our mass in grams. So in equations like PeV equals nRT for our pressure and our gases and that stuff, the N symbol signifies moles. So that's something we would need to convert to moles. But in this case, we're talking about mass in grams. Yeah, good question. How is it 275K if it's in Celsius? Well, so basically the change is going to be the same, right? So we're adding 270, we're adding the same value to change it to kelvins, and then once you take the difference, it's going to be the exact same change. So the change will be 275 in Kelvin and in Celsius because you're adding the same number. Does that make sense? So the change should be the same in both senses, yeah. So convert these numbers to Kelvin first, and then take the difference, and then it's the same number. Okay, so let's go ahead and do this next one. I'm gonna have to skip down past all this. Okay, so this is my next one. I believe it's number 6 on y'all's packet. So oxyacetylene torches produce such high temperatures that they're often used to weld and cut metal. When 2.5 grams of this compound is burned in a calorimeter with a heat capacity of 10.35, the temperature increases from this number to this number. What is the change in energy of this combustion reaction? So when y'all are done with this one, go ahead and let me know, and then we will talk about it. Quickly, for those that are a little bit stuck, what that's perfect. That's the question I was just about to ask. What equation are we going to be using for this one, and why? If anybody knows. Okay, so it's not quite MCAT, and the reason it's not MCAT, which it's a common mistake, so it's not. Yeah, exactly. It's a common mistake. So that's why we need to make sure we're reading these problems really thoroughly. Notice here it says bomb calorimeter, and another good signifier of it is that it says heat capacity. So when we're doing heat capacity, just heat capacity, not specific heat, heat capacity and bomb calorimetry, we use Q equals C, or capital C, which is heat capacity, right? Delta T. So we do not incorporate mass in our bomb calorimeter problems, okay? Does that make sense to everybody? So here, I'm gonna start this one off fast. So this is the equation right here. Q equals C delta T, and this is a capital C. I usually put my double lines underneath it, but I kind of forgot this time. But my double lines mean it's capital, okay? And then also it's good to remember that Q cal is equal to the negative of cube reaction, okay? So let's go back up here so we can read the problem, and then we'll work it out a little bit later. Yes, Q equals MCAT is coffee cup calorimeter and specific heat capacity. Q equals capital C delta T is bomb calorimeter and, bomb calorimeter and heat capacity, sorry. So for this equation, so for this problem, does grams mean nothing? Okay, so that's not necessarily the case, just because we're looking for the whole problem itself isn't looking for Q, right? We're taking it one step farther. We're taking it to energy. So you will need to be using this grams that they give you, but you won't be using it in your Q equals C delta T equation. You'll be using it to help you find energy in kilojoules per mole. So it is important for this problem, but not for the Q equals C delta T equation, okay? So you have to kind of be careful. And then what words were we looking for? Let me just type them out for you so that you can read them instead of just listening to me talk. So for coffee cup, we need to make sure that we're using Q equals MCAT. Okay, remember the A in MCAT is the delta T. And that C there is our specific heat capacity. So if they mention specific heat capacity or coffee cup, you know that you're using this equation. Okay, so that's for that one. And then for bomb calorimetry, right? We're using delta C, or Q equals, I'm losing my mind. Capital C is what I meant, delta T. Okay. And then the word that you should be looking, one word you should be looking for is capital C, right? And heat capacity. Does that help? Okay. So again, you can put an A there and it could just be cat if you wanted, but just notice we're not using the mass for finding our Q, okay? Yeah, they're the same. I can just adjust this. Where our A means delta, yeah, or change in. Okay, it looks like a couple people are done. We're going to wait for a couple more people, and then we'll go ahead and review it. Okay. Does anyone want more time? All right, so let's go ahead and just talk about this one. So like we said, we should be using our Q equals C delta T, right? So I'm just gonna go ahead, I did my work down here below again. So I'm gonna have to go ahead and just start down here. So Q equals C delta T, remember capital C. And this is also another good equation that we need to remember. So first things first, with this problem, I just put in everything I did know, right? Remember, the change in my temperature, even if I converted both of these to Kelvin, the change would be the same. So I just kept it in Celsius, okay? But the change will be the same. So that's why I did it here. If it makes you more comfortable to convert these individually to Kelvin and then take the difference, that's totally fine. It's whatever makes you comfortable. And then this is my heat capacity, right? Capital C. And then when I found those, I found that my Q cal is 124.9 kilojoules. And then we need to remember that when we're talking about our calorimetry, all the numbers that were given in the problem all apply to our calorimeter, right? We take the temperature of the calorimeter. The heat capacity is always of the calorimeter itself. So we take all of this information is in terms of the calorimeter, meaning we solved for the heat or the Q cal. However, we're never focused on the calorimeter. We always care about the reaction. And that's why we have to take the opposite. Because remember, if we're talking about system versus surroundings, whatever happens to the system is the opposite of what happens to the surroundings. So we always have to give it the opposite sign. So because our system here is negative, it's opposite of our surroundings, which is our calorimeter is positive. So that's why we make this value negative, okay? All right, so Q reaction is negative 124.9 kilojoules, and that's what we're focusing on. We don't want this positive value anymore. So the next step, remember, we're not solving for Q, we're solving for delta E, our energy, and it's asking it for it in kilojoules per mole. So that's what I went ahead and did down here. Okay, remember our delta E, they give it to us basically. We don't need to have a specific equation. We know it's supposed to be in kilojoules per mole, right? We have our kilojoules, but it's wanting divided by moles. So I input my yes, that Q cal equals negative Q reaction is the same for Q equals MCAT. Yeah, it's the same for any calorimeter problem. That's just a constant through any calorimeter problem. Yeah. So for this one, again, I just brought down my kilojoules, right? Negative 124.9 kilojoules, but I needed to solve for my moles. And like I said above, we are using that 2.5 grams, right? That's what we're going to be using. It's in grams, so I went ahead and just converted it to the mole form. So I converted to my mole form, which is 26.04 grams. And then that got me 0.096 moles. I went ahead and stuck that back up here because it's supposed to be my kilojoules divided by my moles, right? And that got me negative 1301.0 kilojoules per mole. Does that make sense to everybody? Do I have any questions? It's kind of like a two-part question. I'm just going to always be emphasizing the fact that you really need to be paying attention to your units because your units will tell it all. If you, even if you're tempted to stop at this point, just know that the units they're asking for is, the unit they're asking for is kilojoules per mole. So that would be why we have to go one extra step to find kilojoules per mole. Okay, so I've got a question. So for our bomb, we're pretty much doing a two-step problem, right? Well, it depends on where they ask you. They could just ask you for the Q of reaction, and then you would stop here and this would be your answer. But because the problem that was asked of you right now was asking you for delta E or the energy, you have to take it one step. So for bomb calorimetry, it could just be this first step. It just depends on what the question asks. And then another question, so we changed it to negative because it asked about the reaction instead of the calorimeter. So yes and no, your problems are almost always going to be referring to the reaction. So it doesn't need to explicitly say that we're talking about the reaction, but we should know that the reaction, a lot of the time, especially when I was going about and explaining this in my sessions, when we were going over this for your, I think it was your third exam or your second exam, but it doesn't really matter. When I was explaining this, I talked about this, the difference between your system and your surroundings. Your system is what you're always focusing on, right? Your surroundings are there, but we focus on our system. And in chemistry, oftentimes our system is our reaction. So we always care about our reaction. So even if they don't specifically say we're thinking about our reaction, you should be thinking about the reaction, okay? We're gonna solve for calorimeter, but we need to make sure we convert it to our reaction because that's what we care about always in chemistry. Okay, any other questions on this one? So when it asks for delta E of either coffee cup or bomb, we would do this type of, yeah, exactly. So that's a great point. They could technically be asking for this in the problem that we just did about coffee cup calorimetry. They could ask you to take it one more step to find the energy. And you would do the same process, right? Make sure it's in kilojoules or whatever units it's asking for. You may need to convert out of kilojoules. It just depends on what they ask for. And then divide by the moles. And they should give you enough information to do that. So we always change it to reaction is what you're saying. Yeah, I would always change it to reaction unless they explicitly say calorimeter. Like if we're talking about what's the Q of the calorimeter, if they say that, then keep it in calorimeter. But they rarely do that. And we always do Q of reaction. But they would explicitly say, what is the Q of the calorimeter in order for that, in order for you not to change it, okay? Does that make sense? It's just really important to make sure you read through the problem thoroughly, circle important words, make notes to yourself so you don't miss anything. Okay, so I know you'll probably saw my answer to the one above this, but we're gonna act like we didn't and focus on this one. So will a precipitate form when 1 molar or 0.1 molar aqueous solution of CrCl3 and NH4 2S are mixed? If so, identify the precipitate and give the net ionic equation. So go ahead and do this one and then select your multiple choice answer for that and let me know what you guys get. And this one's strictly just knowing your solubility rules. Okay, so let's go ahead and talk about this one. What answer choice did y'all select as the correct one? Awesome. So that is exactly what I got too. So just notice, I did narrow it down to C and D, but then you need to make sure you're paying attention to those subscripts and make sure they match up correctly, okay? But it looks like y'all got that 100%. So C is the correct answer. Do I have any questions about that one? All right, so let's go ahead and do the next one, which is down here. Okay, the hybridizations of nitrogen in NF3 and NH3 are blank and blank respectively. Which answer choice do y'all believe is correct for this one? And for those that are maybe stuck on this problem, can anyone tell me, there's a nice trick that we use for hybridization and determining the type of hybridization. So can anyone tell me what it is, what we look at on an atom or in a compound, more likely? Yeah, perfect. The bonding groups, right? Exactly how many things are on the central atom. So we look at the number of bonding groups, and the number of bonding groups tells us our hybridization. So I'm going to wait for a couple more answers, and then we will discuss about which one is the correct one and why. Yeah, no worries. So the trick to these problems is really just looking at the number of bonding groups around the central atom. So in this case, because we're talking about hybridizations of nitrogen, it is the central atom. So we're going to look at how many bonding groups. No, they don't. It's hybridization really talks about, when we're talking about hybridization, we like to talk about bonds because that's what's creating the hybrid. Does that make sense? We are bonding two different atoms together, creating a bond, and that's the hybrid. We're bonding two orbitals together. So let's just go ahead and talk about this one. So if we're looking at NF3, how many bonding groups does it have? 3. And it's also the same as in NH3, right? There are 3 bonding groups, correct? So to answer this one, when we're looking at these problems, I'm just going to go ahead and scroll down. The correct answer is D, and here's why. So remember, we can just count however many orbitals, so to say, we have in each of these. So if you look at this one here, we have 2 p orbitals and 1 s. So 2 plus 1 is 3. So does that make sense? Okay. I thought we did count lone pairs. You count lone pairs when you're determining shape, but not necessarily when you're determining hybridization. And you also use the valence electrons as lone pairs to determine like its orbital diagram and all of that. But for hybridization, it should just be, yes, double bonds count as one group. Okay. The way I always looked at it is when we're doing these hybridization problems, we're looking at the formation of a hybrid between two different bonds. So for tetrahedral shapes, it's sp2. So it's going to be sp2 if it has 3 bonding groups. Yes. Shape, okay, yeah, so they're okay. Tetrahedral is sp3 because it has 4 bonding groups, but the electron is not a bonding group. Does that make sense? So it's an electron group, but not a bonding group. Okay, and Google says NF3 is sp3. So this, okay, I don't want to argue with Google, but this did come off of one of a previous exam, and this was the answer on the answer key. So I can't really argue with Google, but this was on a previous exam, and this was the answer on the answer key. So that is my, that's my backup for this problem. Yes, lone pairs are not bonding groups because they are not bonding to another atom. Lone pairs affect the shape, yes, but bonding groups are what we talk about in hybridization because they are basically combining. Yes, that's why we don't count it. They are combining 2 different orbitals. Our electron groups are not combining 2 different orbitals. They're just present. So they do have an effect on the shape, but they don't have an effect on our hybridization because hybrid is basically combining one atom's orbital to another atom's orbital. Okay. All right. Hopefully that makes sense. I did not make this problem up either. So this was on a past exam, and this is from the answer key. Okay, hopefully this makes sense. It is kind of a tricky concept, but remember, electron groups and bonding groups are very different things. Okay? All right, so let's go ahead and talk about 24. What is the orbital hybridization for the phosphorus atom in PCl3? It's kind of just a repetitive one. And I think that there's a typo on these. I don't know why my D's got put before my SPs. They should be on the end. And I think it just happened with my Word document. I don't really know what happened. So they are out of order. That's not intentional. That's a mistake. So this one should be really repetitive just because we just talked about it. But it was also a question on, I believe it was on the same exam too. So. And what answer choice are y'all putting for this one? Perfect. Okay, so yeah, that should be your answer for this one. Remember, we have 3 bonding groups. That's going to affect your hybridization, and that should be 2p and 1s, which add up to be 3 as well. So 3 bonding groups. Okay, let's go ahead and look at that one. So give the electron or ground state electron configuration of Se2-. So again, if there are lone pairs on the PCl3, that is not going to affect its hybridization. That'll only affect its shape. This question is asking about hybridization, not shape. And then what do I mean by 2p and 1s? So really, a good way to remember these is you can add up the exponents. So if you throw in an exponent of 1 right here, so it's S1P2. If you add up those 3 numbers, it's going to add up to the number of bonding groups you'll have. So that's what I'm saying here. We have an exponent of 2, meaning we have 2 p's or 2 p orbitals. And then we should have, it's not written in, but we know that there's 1 s, and that's going to be accounting for that 3rd orbital. We have 1 s orbital and 2 p orbitals. Okay. Okay. And what answer choice are y'all putting on this one? All right. So when we're looking at this one, a good way to, we just have to identify where Se is on the periodic table, right? And then we're going to want to make sure we're including that -2, which is an addition of 2 electrons. So at that point, I would just move 2 spaces to the right? And then we'll formulate the electron configuration for the Se 2 spaces to the right. So remember, the 2- means we're adding electrons. We can remember this because electrons have a negative charge, and the more negative we get, that's going to be this number here. It symbolizes the more negative we're getting, the more electrons we're accepting. So the answer for this one, y'all had it right, was D. And just kind of notice I wrote out some things that what I was thinking through when I went through this problem. On the periodic table, this should be just Se with a 0 charge, just the neutral Se, right? However, we added 2 electrons, meaning we needed to increase this number by 2 to get us 6 electrons in that valence shell. Okay, any questions? So that's going to be electron configuration. So the question was, what is it called when you have to write it all out, like beginning from 1s, 2s? That's just basic electron configuration. What they have written here is condensed electron configuration. If they ask for condensed, you use your noble gas, right? However, if they're just asking for regular electron configuration, like in a free response problem, right? If they just ask for regular electron configuration, you need to write out the full thing. If it's asking for ground state, you can, or not ground state, if you're asking for condensed, you can start with your noble gas, okay? But it doesn't really matter for this problem because it's multiple choice and they're all in your condensed electron configuration. Okay, yeah, so for valence electrons, remember the rules for valence electrons was only S and P orbitals. So a good way to, this is a great example of doing this real quickly. So everything from argon to the left, right, on the periodic table, or anything from argon lower in energy is considered an inner electrons. Anything from argon to the right or argon forward, which includes S, D, P, sometimes F, those are considered outer. Your valence electrons are everything from the noble gas or argon to the right, but only S and P. So we ignore our D for valence electrons. So in this case, Se2 minus would have 6, 7, 8 valence electrons, but it would have 18 outer electrons. Does that make sense? Okay, yeah. So let's go ahead and do this next problem. Which of the following below represents the second ionization energy of SR? And y'all can just go ahead and type that answer into the chat when you have it. Okay. So the answer to this one, yes, is D, and we'll kind of talk about why. On y'all's, it should be corrected. There should be an electron that I added in there, but on my key, I forgot it. So that's why I have it written in. But it should be correct on your packet. I made sure. But remember, when we're talking about ionization energy, we're going to always have electrons as a product, right? And then the next thing you need to pay attention to here is the second, right? This means we have already removed one electron, meaning we need to start off with a positive charge because we've already removed one electron. And what second ionization means is we are removing a second electron, right? Now, they may put a question on the exam where maybe, or not a question, but a multiple choice question, where it says a 2E right here, and that's one of your answer choices, and that will be incorrect because you need to make sure you're counting up these charges and making sure they all cancel out, right? We need to know that it's +1 charge on this side, which means total on this side, it also needs to be +1. So a +2 minus this 1 gives us a +1 charge, okay? So there will never be a coefficient before your electrons when we're talking about ionization energy because we're removing one at a time and because your charges need to add up. If you put a 2 right here, before your 2 on the electrons, it would be 2 minus charges and a 2 positive charge, which would cancel out, giving you +1 on this one and 0 on that side, and that is incorrect. Okay, so yes, total you have removed 2 electrons, but you've removed them in 2 different steps, and that's why we don't put the 2 here. Okay, I've seen that on an exam before, that's why I'm talking about it, but again, with ionization energy, your electrons will be on the product side. Now, with electron affinity, your electrons will be found on the reactant side because remember, we're adding electrons. So think about it in terms of a reaction. Electron affinity, we are adding electrons, they need to be a reactant. However, with ionization energy, we are producing electrons, right? This is the process of getting rid of an electron from SR and producing it. So that's why they're on the product side. So for ionization energy, your electrons will be on product side. For affinity, they'll be on the reactant side. Okay. Any questions about that one? This next one's more conceptual. I mean, this one was also pretty conceptual as well. So the volume of a gas is proportional to the temperature of gas is known as which of the following laws? What answer choice did y'all select for this one? Or would you select? Y'all can take a minute if you need it. Okay, perfect. So y'all are all saying C, and that is correct. Sorry, let me go scroll down. So I kind of wrote out why each of them are. So Avogadro's law, remember, is the relationship between volume and moles. My way of remembering that, when I'm thinking about Avogadro's number, we know that it's a conversion between moles and number of entities, and this is the only one of these laws that has to do with moles. So that's how I remembered Avogadro's law. Ideal gas law, PV equals nRT, it's all of them. Charles' law is the one that deals with volume and temperature, and Boyle's deals with pressure and volume. Okay, so that one's just strictly memorization. There usually aren't too many problems about like actually knowing which law is which, but sometimes I do see them throw it in there just to kind of test how you know. Dalton's it shouldn't apply to this problem. It was just kind of thrown in there. There's a Gay-Lussac's law. Yeah, ideal gas law is PV equals nRT. You're good. Okay. So let's go ahead and scroll down to this next one. Kind of a big gap, sorry. Y'all just saw the answer, but that's okay. So a 14.01 gram sample of N2 reacts with 3.02 grams of H2 to form ammonia. Please remember your differences between ammonia and ammonium, okay? And then if ammonia is the only product, what mass of ammonia is formed? So go ahead and take a minute, and you can just type your answer in the chat when you're done. Does anybody have an answer for this one? Awesome. Okay, so yes, the correct answer is A, and I'll just go ahead and show you my work real fast. So they are very specific that this is the only product formed, so that's why you're able to form a reaction and balance it, right? And after balancing it, you need to, it's just another example of a limiting reactant, okay? So we started with our 14.01 grams of N2 and converted it over to our NH3, which gave me about 1 mole. And I did the exact same thing for H2, which also gives you about 1 mole. Because they're equal, it means the reaction is going to be basically the same. So that's why I had more space after this 1 mole than I did over 0.99. So that's why I chose to do it on this 1 mole, but it doesn't, you would get the same answer either way. So yes, technically this one's a little bit smaller, but your answer again with rounding and all that, it's going to be the same. So that's why I did it on the top one and not the bottom one, because technically here we don't have a limiting reactant. So don't get confused by why I chose that top one. And you should just get 17.01, okay? Just about, with maybe some rounding differences. On the exam, if they were asking if it was like free response and they asked you to use significant figures, then I would probably use the bottom one, because if we're talking about significant figures and we're going down to like, the specific decimal places, this one would give you the more correct answer. But if it's just multiple choice, they're not going to give you an answer that's so close between the two, right? Okay, do I have any questions over that one? Okay, because we've already done a whole bunch of hybridization, I'm not going to talk much about this one. I am just going to give you the answer. I'm going to try and get to this next problem. I'm trying to get through them pretty quickly because I want to be able to explain the harder ones. So the answer for this one was just one, and it's all based on those bonding groups, right? The rest of them this one has 4 bonding groups. These ones both have 5 bonding groups. The only one that matches this one here, which is 6 bonding groups, right? We have 3P, 2D, and 1P, which comes up to a total of 6 bonding groups. There's only need 1. So that's why I put that one on there. But the more important one, not more important, but the one I want to get to here is number 15. Determine the empirical formula for a compound that contains C, H, and O. It contains 52.14% by carbon and 34% oxygen. Go ahead and solve it just real quickly. When they're giving you these out of this, and they left out hydrogen, obviously, what you can do is assume that we're doing it out of 100. And so I just took the difference, right? I added up my carbon and oxygen and subtracted it from 100 to get my 13.13. So it's 13.13% hydrogen, which is what was left out. Okay, so when y'all have done this one, go ahead and type your answer into the chat, and then we will discuss. Does anyone have an answer for this one? Do you remember how to find our empirical formulas? Okay, So let's go ahead and talk about it. Let's jog y'all's memory. So remember, one of the rules for empirical formulas is if they give it to you in percent, you can assume that it's out of 100 grams of sample, okay? Sometimes they give you, instead of percent carbon or percent oxygen by mass, sometimes they give you actual grams, or sometimes they give you actual moles. But in this case, they give us percent, and so we need to assume that it's out of 100% gram sample, okay? So with knowing that, we can automatically just convert each of these numbers straight to grams. So 52.14 grams, 34.73 grams, and 13.13 grams, okay? So the next thing we need to know is that, yes, we like to, once we've gotten into grams, we don't like to work with grams. We like to get into moles, right? That's all of chemistry. We tend to work in moles because they're a lot simpler and easier to understand. So that's the next step, okay? So that's what I first did. When I'm doing these problems, I like to set it up like this. So this is my grams, right? So that's why I put the grams here. And then I set up my basic setup, right? It's going to be C with some subscript, H with some subscript, and O with some subscript, okay? So first things first, like I said, I put my grams here, 52.14, 13.13, and 34.73. Underneath, I put the conversion. So you can write out the conversion if you want. So if we're going from grams to moles of carbon, right? Or sorry, I mixed these two up. It's supposed to, hold on. Before I confuse y'all, I'm so sorry. I just realized this and I don't know how I messed that up. Let me, so sorry. So let me cover this up real fast. So it's supposed to be, okay, oh goodness. This right here is not supposed to be 16. That one's supposed to be 12 and this one's supposed to be 16. I think I just swapped it and I really don't know how. So I'm so sorry about that again. So remember, carbon's mass is 12, right? So I'm going to divide by the mass of carbon to get me my actual number, which is 4.3. So do you see how I'm kind of working this out? 52.4 is my gram sample. I'm going to do a conversion and convert it into moles. So 52.14 divided by 12 is going to give me my moles, and that'll be 4.3 moles of carbon. Okay, so I'm kind of working vertically. You can work it however you want. You can do and I'm going to get there. But you have to make sure that you are getting into moles first. So this is in grams, 52.14 in grams, and then I'm going to convert to moles. I'm going to convert to moles by dividing it by 12, okay? You can do it like this if you want. You know how we used to do, or you can still do it like this, but you did 52.14 grams, right? And then we're going to multiply this by the fraction, right? Which is, if we're going to do a molar mass conversion, we know that 1 mole over my grams on the periodic table, 12 grams, is my conversion there, right? So then I'll solve that, and that'll give me 4.3 moles. Does that make sense? So you can do it, and you can do stoichiometrically like that if you'd like. For me, this worked out for me, so it's just based on what you like. But if you do each of these the same way as this, you'll get 4.3, 13.13, and 12. I mean, sorry, not 12, 2.2. Does that make sense to everybody? So 16 would go underneath this one. So do you all understand how I got these numbers? Yes? Okay. So again, you just do this. You convert them to moles. So we get 4.3 moles, 13.3 moles, and 2.2 moles. Now you divide by the lowest value, right? Now that we're in moles, you divide by the lowest value of the 3. So because 2.2 is the lowest value, we're going to divide each of them by 2.2. Now that we're in moles, you must get to moles first. Okay. So I'm going to divide 2.2 by 2.2, and that gets me 1. 13.13 by 2.2 gets me about 6. And 4.3 divided by 2.2 gets me about 2. Okay, so that's why A is your answer. So I'm sorry if this setup kind of confused y'all at all, but real quickly, if you really want me to, I can go ahead and just do this to make sure that we're all on the same page. This is my carbons. I'm going to do hydrogen next. I'm going to start off with 13.13 grams, and I'm going to multiply that by my 1 mole over about 1. It's 1.008 grams, and that should get you the same answer, right? So that should be 13.13. Okay, so that's how I got this 13.13 here, and then the same process for oxygen. Do you guys want me to write out the oxygen one? Okay, perfect. So that's that's a review of your empirical formulas. Okay. Let's go into this next one here. So this was some more review about your orbitals and quantum numbers. So give the numbers of m sub L for a p orbital. What answer choice do y'all think is for that one? Perfect. This one should be really fresh on y'all's mind considering this is your last exam, right? Perfect. So the answer for this one is B. Kind of wrote it out. Remember, p orbital is aligned with an L of 1. And then for an L of 1, our m sub L values are a range of -1 to +1. Okay. Go ahead and do this next one. Find the volume of a 5.6 gram of O2 at 7.788 at ATM, and 415 Kelvin. And then when you have done that one, go ahead and type your answer in the chat. Perfect. Okay, yeah. Let's go ahead and talk about this one. This is a PV equals nRT equation, right? So that's the equation I've listed here. Also take note that we're dealing with an N, meaning moles. That's why I did the mole conversion over here. So it's 5.6 grams. And I did a conversion, remember, O2. So that's why it's 32 here. And I got 0.175 moles, which is what I plugged in. So we have 7.78 atmospheres times an unknown volume, 0.175 moles, and then remember our gas constant, and 415 Kelvin, and that should get you 0.766. That's not a 1. I don't know why the scan picked up a line there, but it's 0.766 or E. Okay. All right. Let's go ahead and do, hopefully 18 is not too tricky. They do usually put some of these problems on there, but hopefully it's nice review for y'all. Which answer choice do y'all believe is correct for this one? Perfect. Right, just some review from the very beginning. Phosphate, your polyatomic, should have a charge of what? Anybody? Perfect, -3, right? So that's why this one's our answer. This -3 would be up here. So -3 and a -2 charge for magnesium. Okay. Let's do, which hybridization scheme allows the central atom to form more than 4 bonds? And like I have right here, there are 2 correct answers. So if you were looking at this one thinking, I'm crazy because there's more than one answer, there is more than one. So that was just kind of my mistake when I was, yeah. Okay, yeah. Perfect. So just remember, your d orbital usually allows you to form more than 4 bonds, right? So that's why when we say atoms in the d orbital can allow for an expanded octet, that's why. So I usually just kind of count up my orbitals, right? We have 3p and 1s, which is 4. We have 5 possible here, 3 and 6. This one and this one allow for more than 4 bonds, okay? And that's because they are an expanded octet using the d orbital, okay? And this one, my key kind of gives you the answer, but which molecule would you expect to be a free radical? And like I said, odd number of valence electrons is usually what you look for when you're dealing with a free radical. A free radical. So a free radical is an atom. So for just an example, it's an I'm going to just write, yeah, look for an odd number of valence electrons, So basically a free radical is an atom that has an unpaired electron. So on its valence shell, you would see, like, if we're talking about maybe, it's not gonna be 100% accurate, but let's just, oxygen's common. And remember, when we're drawing a structure of, actually, let's do nitrogen. Nitrogen's correct, not oxygen. So we go ahead and just draw this, right? Nitrogen should have how many valence electrons? Should have 5, right? So we're gonna go ahead and draw those. We're gonna have 1. I'm gonna draw lines just because, okay, wait, maybe I won't. I'm gonna draw lines because that's all it's gonna let me do, but it's gonna have 1, 2, okay. Oh my God, okay. Let's just do this. So it's gonna have 1, 2, 3, 4, or 1, 2, okay, you know what? I can't draw this. Basically, it means it has an unpaired electron. So it's going to have, in a compound, it's going to have one of them have a single electron on it, okay? Because it's not working, I wanna look at a picture so I'm not confusing you, I know. Hold on 1 second. I wish I could, it's like, exactly, so it's a lone electron, not a lone pair. That's a perfect way of putting it. So, I wish I could draw better on this thing. It makes it really difficult that I can't. Let me see if I can find a good picture. I'll show you guys at the end. Let's get through some of this. If you want to see what it looks like, stay for the end and I'll find it, okay? But for this answer, it should be NO2 because it has 17, or an odd number of electrons, meaning one of those electrons will be alone and not in a pair, okay? So yeah, it's a perfect way of putting it, a lone electron, not in a lone pair. Okay, let's go ahead and move on. I will find a picture of that for you after if you want to stay. So choose the correct equation for the standard enthalpy of formation of CO. Go ahead and type your answer in the chat for this one. Yeah, good question. GR is abbreviated for graphite. So there's 2 options for carbon. Carbon has 2 forms. We don't really say it's solid or any of that. We go graphite in its diamond form. So diamond, as we know, is extremely stable and it's not reactive. However, graphite is. So in these compounds, graphite is what we're going to be using to react with things. Okay. Okay. And real quickly, I found a picture, so I may as well just show y'all right now. But this is a picture that I found right here. So if you guys can see this right here is an example of a free radical, where usually stability would mean you have 2 electrons here on the outside, but because there's only 1, that's going to be what defines this free radical. Okay? Does that make sense? Okay. Sorry it took me a minute to find the picture. It wasn't loading what I wanted it to. So let me go back to my key. So how do we know it was NO2? NO2, again, it's going to have an odd number of electrons. And if there's an odd number of electrons, one of them won't be paired. And that's how we know. So you could look at it on an actual picture and pick the one that has an unpaired electron, or you could count the number of electrons and pick the one that has an odd number compared to an even. Yes, great question. You do add both elements valence electrons to see if it's odd. Yeah, so that's how I got each of these numbers. Okay. These numbers are the additions. Sorry if I wasn't clear on that. Okay, so yeah, I saw some correct answers for this one. The answer for 21 should be B. And then after this problem, I'm just going to give you the rest of them. And if you see one that you want to be explained, you can let me know. But the explanation for this one, remember for enthalpy of formation, the standard enthalpy of formation, we only want 1 mole of product, okay? And this one here is the product, CO. So that's 2 things we need to take into account. We need the CO to be in the product side, right? That's why I crossed off A. And that's also why I crossed off E. After I look at what's on the product side, I need to think about, I only need 1 mole of it, okay? And that's what standard enthalpy of formation says. We only look at 1 mole of the product, right? So that's why I cancel out D. So then I'm left just to B and C, and the answer just comes down to determining which one is appropriately set up, and it's not balanced correctly at all, right? So that's why we choose B as our answer here. Does that make sense to everybody? Okay, so before I work through any of them, I'm going to go ahead and show my answers and works. Hold on. So the reactants should have only 1 mole. Not the reactants, it's only 1 mole of product, okay? So you can manipulate the reactants coefficients to make sure there's 1 mole of product at the end. But you can never have a coefficient here. It needs to be 1 mole of product, okay? So a good example would be this one, they've already manipulated it, but in order to do so, they would have had to put a 1/2 here so that we can get rid of a 2. Does that make sense? So this one's already set up appropriately, but we have to have 1 mole of product, and that's why I got rid of this one here. Reactants you can manipulate. Okay, so I'm just gonna go ahead and show you these. So this is 22 and 23. Why wouldn't O be O2? Because it technically would, but if you showed the beforehand, like that, the equation that we were just looking at was the total completed solved one. So in the process of solving it, we would have had an O2 there, but in order to manipulate everything else, we would have added a 1/2. So I can kind of show you what I mean real quickly. I'm going to scroll up on this. So when we're solving this one, actually, I want to show you, I'm going to go down real fast and answer your question. There's a problem down here. It's like this one here. So originally we have an O2 and we have 2O, but it's asking for the formation of oxygen, right? So I have to flip my equation so that oxygen is on the product side. Okay, and now that oxygen is on the product side, I need to know, well, if it's my enthalpy of formation, I need to make sure I simplify it. I can't have 2 here. I have to have it just simplified to 1 mole of product, right? So that's why I divide it by 2. Now, if I divide this side by 2, I also have to divide this side by 2, okay? Which means I have a 1/2 on this side. Now, technically, 1/2 O2 is equivalent to just oxygen. So I have gotten rid of one of those oxygens. So in the equation that I just did above, that's assuming that they already did this work before you. So they gave you the most simplified version of that equation. So you could simplify this even down to just O to O, okay? So oxygen is there, but they have done the work beforehand to get rid of one of those oxygens. Okay, sorry to scroll down on y'all. So I was right here. Hopefully y'all saw 22, here's 23 and 24. Okay, I'm gonna go ahead and scroll down. Here's 20, try and squeeze, no, it's fine. 26 and 27, I'll scroll down in just a second. Okay, here's 28. Notice for 28, I did a -1 here. I multiplied it by -1 because the work is done by the gas, meaning it's going to be a negative sign, right? We're doing work done on the surroundings, giving it negative. So yes, there's a negative incorporated into this equation, but we have to make sure we're adding an appropriate negative because work itself is negative. So I have to change the sign. That's why I changed the sign there, okay? All right, I'm gonna go ahead and scroll down for 29 and 31. I kicked out a problem there. That's why my numbers switched, but it should be in order on your packet. Okay, I'm gonna go ahead and move down. Here's 33, or I think it's 32 on your packet. And that should be it. Okay. Good luck on all y'all's finals. Thank y'all for coming to my sessions. I'm gonna miss having y'all on my sessions. I always get really sad during my last session, but it's been an honor to help y'all. So always let me know if you need anything. I will be answering my emails. So if you do have questions, feel free to email me and I'll do my best to respond. But other than that, y'all have a great and safe break. Stay healthy and good luck on everyone's finals. Let me go back up to 25. That should have been this one here. There you go. Y'all have a great night. Okay, I'm gonna go ahead and scroll up to, I think on y'all's packet it's 16 through 20. So let me scroll up real fast. That should be right there. Okay. So there's 16, 17, and 18. And then I'm going to go ahead and scroll down for, so I see this one. Okay. So there's 16 and 17. And then my work is kind of split up. So my work for 19 is down below. So that's the answer for 18. My work for 19 is right here. Sorry, I've got it split up. My work for 20 is right there. Yeah, of course. All right. For those of you that are still here, do y'all have any questions I can answer? Anything you want me to go show you on the key again? Yeah, of course. All right, so I'm gonna go ahead and head out. If y'all do have questions, feel free to email me and I'll do my best to respond. But yeah, have a good night. Y'all be safe.